Okay, we're on our first lesson for this whole online digital learning thing. This is for pre-calculus honors. We're doing 7.1 solving systems of equations. So you should have this open up in your Notability and you can take notes as I do it here. So this is something you have some background on, so it should be doable. A linear system or system of equation, that's what goes in this first blank, system of equations, is a set of two or more equations using the same variables. And then a solution set consists of values for the variables that are solutions of each equation of the system. Now there's different methods to solve: graphically, substitution, elimination, sometimes they call that linear accommodations, or matrices. I'm not sure if you know how to do that with matrices. That's something we're going to look at in this unit. As far as categorizing systems by names, if the lines intersect, you know what a graph looks like. The lines intersect. Let's say one's going this way and the other one's going this way. Then there's a point where they intersect and there's one solution. The name of this system, this is what they call a consistent system because it has a solution. And because there's only one, it's independent. Parallel lines, on the other hand, you know what they look like. They like this. They don't cross at all. So there's no solution. You know, they don't have a solution. This one's inconsistent because it doesn't cross at all. So there's no solution. Coinciding lines, I don't know if you've heard that word before. That just means the same thing as same line. That if you graph it, you actually end up with one line because it's the same. It's like the same equation, just written in a different form. That means there are infinitely many solutions. Sometimes you see it written as IMS. I write that a lot because I don't like to write a lot. This one is consistent and dependent. So it's a little bit, let me spell that right for you guys. That's a great thing about erasers, y'all, and writing in pencil. Okay, and dependent. So what we're going to do now is look at solving a system by elimination. That is probably the fastest way, and I like it the best. Sometimes I use substitution. It kind of depends on how they give me the problem. So this should just be review for you. You've done this a lot. So on example 1, our goal is to eliminate one of the variables. You can choose X, you can choose Y. It really doesn't make a difference. I normally choose the one that has, if there's one that has a coefficient of 1. So I'm choosing to isolate, I'm sorry, I shouldn't say isolate, eliminate the Y. So I'm going to multiply this top one by -5. So that would give me -15x plus 5y equal -35. Remember, you go across the board, even the one on the other side. The second equation, I'm just going to bring over. And now I can add these two equations together and one of them cancels. The y's cancel, which is what I want. -35 plus 9, that's -26. Divide by -13, so I know x is 2. So once you know the first one, then you plug it back into either one of the original ones. I'm going to choose the top one, the top equation. It really doesn't matter. You get the same, or you should get the same answer either way. All right, so y would be -1. So our ordered pair is 2, -1. Now you can check it by plugging it back into the equations. I'm not going to make it mandatory. It's up to you if you want to do that. All right, the next page. Example 2, inconsistent and dependent systems. So on this one, this is showing you what it's going to look like if they're different. Okay, so you can use substitution, you can use elimination, it really doesn't matter. There's multiple different methods to do this. I'm going to multiply this bottom equation by -3 to cancel my y's, just because that y has a coefficient of 1 on the bottom. So that means my top equation's not having to change. The bottom one, if I multiply everything by -3, that gives me that. So when I add them together, notice the x's cancel out and the y's cancel out. So I'm left over here 0 on this side, and the other side I'm equal to -1. But that's not true. 0 is not equal to -1. That means this really has no solution. This is what it would look like algebraically. Obviously, they're parallel lines, because if I graphed it, it would be parallel. So it's inconsistent. If you want to write parallel lines there, you can, because it obviously is. So that's an inconsistent system. Now, on example 3, it says solve this system. I'm going to multiply this one by 2 to cancel the y's again. I like to work the ones that have a coefficient of 1. So that gives me 6x minus 2y equal to 8. On the bottom, I'm just going to bring that one down. And notice what happens on this one. The x's and y's cancel out again, so I get 0 on this side, but this also goes to 0. And that's a true statement. So this means there are infinitely many solutions. A lot of times I just put IMS on there like this, because I don't want to write it out. It is dependent. It's a dependent system. It's a coinciding line. So if I had graphed it, that's what it would look like, meaning the same line. Both equations would represent the same line, even though the equations look different. Okay, so the next part we go into is solving nonlinear systems. So notice that example 4 is not as easy as the others because the others are linear. So I'm very confident you did the linear ones before. Non-linear, not so much. So there's a couple different ways to do it. You can use elimination if you have the same letter that could eliminate. Sometimes you're forced to solve it in a different method because you can't use elimination. So you might have to use substitution. On this one, I'm noticing that there's an x squared in both of these equations. So I'm going to write it where those two line up. So this would be negative x squared plus y equal to -4. So notice I didn't really line up my y squared and my y for the sheer fact that they're not the same. I can't add them. They're not like terms. But the x squareds go away, so I'm left with y squared plus y equal to 12. And now that I see that I have a y squared and a y, so I'm going to have to hopefully factor. This is quadratic now. So I'm going to make this equal to 0. And oh goody, this one does factor. Isn't that what it factors to? Yes. Okay, so zero product property says y is equal to -4 and y is equal to 3. So these are our two potential values here. But now that means we got two different x's, right? If I have two y's, I also have two x's. So let's plug it in. I'm going to go to that bottom equation just because that top one kind of looks a little more difficult. But if I plug in -4 for y and I solve here, that's going to give me 0 equal to x squared, so x is 0. Oops. Here, if I plug in 3 for y, that gives me 7 equals x squared. So if I take the square root, that's positive or -7. So actually, I got 3 points. That means I've got the point 0, -4. I've got the point negative square root of 7 and 3. And then I've got the point square root of 7 and 3. So there are 3 solutions to this one. Because remember, that top one is a circle. And this is like half a parabola or sideways thing. So it crosses at 3 points. Now example 5 says solve by graphing. I'm not going to make you graph solving this by graphing. I would let you use one of those graphing calculators to do it, to solve that system. I'm going to teach you soon how to do this with matrices so you can plug all this in your calculator. But if we did graph it, it's going to look like, let's see, that top one is an x cubed, it was something like this. I'm just going to give you a thing. And then the other one kind of went like that through it. So there were three different points where they crossed. And you would have had to use a calculator to do that, like a graphing calculator, obviously. The ordered pairs where they crossed, if you have yours and you just want to do it, then it is that point and this one and this one. And I'm not going to ask you to do that on anything I assess anyway, just because of our situation. I probably would have done that otherwise. So let's keep on going. Okay, now we're on to solving a system with three variables. And I feel confident you've done this before, but if not, you can just say you heard it here first. Not a big deal. So in example 6, we notice we have three variables, we have three equations. That's absolutely fine. That's exactly what you need. If you have three variables, you have to have three equations to solve it. Otherwise, you can't. So you can decide, do you want to eliminate x? Do you want to eliminate y? You want to eliminate z? Doesn't matter which one you pick. Your work would look different than mine if you chose something different than me, but your answer should exactly be the same. So it's not a big deal at all. I like to choose the ones maybe with the coefficients of 1, or I don't have to change the sign. So, but it really doesn't matter. You can just pick what you want. So I'm going to, I think I'm going to isolate, I keep saying isolate, eliminate the z's. So I'm going to do this first equation and this last one because the z's will cancel out. So let's see, that's x plus y plus z equal to 5, and 3x plus 2y minus z equal to negative 4. So if I add those together, those z's cancel out, which is what I want them to do, and that gives me that. Now I'm going to look at these bottom two, and I'm going to multiply this one by 2. So that gives me 2x minus y plus 2z equal to 1. Underneath there, 6x plus 4y minus 2z equal to negative 8. So if I add those together, I get that 8x plus 3y equals negative 7. So now looking at those two, I'm going to eliminate the y. So I'm choosing to multiply this first one here by negative 1. So negative 4x minus 3y equals negative 1. The other one I'm just going to bring down and put it underneath here. So that gives me 4x equal to negative 8. Now I can solve just for the x, and 8 is negative 2. So once you have that first value, you can go back to either of the ones that have, well, without the z's. I'm going to choose the one that has the 4x because it's smaller numbers, but it really doesn't matter. Either way, you get the same thing. And I got y is 3. And then I just plug into the last one. I'm going to choose that top equation. X plus y plus z is 5 because it looks like the easiest one there to me. And I get z is 4. Oops. So if I write this, normally they put them alphabetical order when they put it together, x, y, z, like that. So that would be your ordered pair, ordered triple, I guess I would say. So let's look at number 7. As another example. Here you can choose to isolate this, eliminate the x, the y, the z. It really doesn't matter. I think I'm going to do the same thing I did on that one. I think I'm going to go with the z's because they look like they're pretty easy to take care of. So on the first one, I'm going to do the first and last, basically the same way I just did that one. And add those together. And if you ever want to pause me or something and do it yourself and then look to see if you got it right, that is totally okay. All right, so this one I'm going to multiply this one by 2. Oh, funny, it's like almost the same steps I'm doing on this one. Now you don't have to do it this way. If you want to do it another way and then try it out and see if you get the same answer, I'm totally okay with that. Actually, it might even be fun. Okay, so, all right, so that's what I got. So at this point, I'm going to eliminate a y. So I'm going to multiply, we'll multiply this one by -1 again. Oh my goodness, this is like the same exact procedures. How odd is that? That's not going to happen a lot, y'all. It's just coincidence, okay? All right, I got x is 1. At least the x value is not the same, right? So x is 1. Then I'm going to choose to plug it back into the one with the smallest numbers. And I got y is 3. And then let's see, I'm going to go with the top one again because that it looks like it to be the easiest. I got z is -2. So that would be 1, 3, -2. Now the next part we are looking at example 8, curve fitting with systems. I'm not sure if you've done curve fitting before. If you haven't, not a big deal. You can say you heard it here first. But basically, we're going to try to find out the values of a, b, and c so that the graph of the quadratic function contains those particular points. So remember, those points are our x and our y's. So we're going to plug it basically into this equation. We're going to have 3 of them, and then we're going to solve that system to find out what is a, b, and c. So remember, this is x, this is y, this is x, this is y, this is x, this is y. So when I plug it in, I'm going to say y, that's 11, is equal to a times x squared plus b times x plus c. That would take care of the first point. Then the second point, that would be 5 equal to a times x squared plus b times x plus c. And then the last one would be 3 equal to a times your x squared plus b times your x again plus c. So if we clean those 3 equations up, then that gives us minus b right there. A minus b plus c equal to 11. Then we have 4a plus 2b plus c equals 5. And a plus b plus c is equal to 3. So once we've cleaned it up, then we can just solve that system. You can cancel a, b, or c, doesn't matter. Since the b's are different signs, I think I'm going to cancel the b's. But like I said, you can do any of them, it doesn't matter. So if I go to cancel the b's, then I'm going to take this first one and the last one. And so that gives me 2a plus 2c equal 14. Now I'm going to use that same system, but now I'm going to cancel the b of it, 2 different ones. I did the top and the bottom, so now I'm going to do these top 2. So I'm going to multiply this one by 2 and use the top 2. So that would give me 2a minus 2b plus 2c equal 22. Don't forget to go all the way across there when you're multiplying by something. Okay, so if I add those, it gives me 6a plus 3c equal 27. Okay, so now I'm taking these 2 equations and I'm gonna, which one you want to do? Yeah, I would do a also, because if I did c, I'd have to multiply both of them by something. But if I do a, I can just multiply this one by -3, and then I can get them to cancel. So this 6a plus 3c equal 27 is not having to change. The other one, if I multiply by -3, 3 times 14, what's that? 3 times -42, thank you. All right, so that gives me -3c equal to negative 15. So C is 5. Okay, that's important. And once we know that, we can go back to either one that has the A and the C. I'm going to choose this one that has the smaller number. So 2A plus 2 times 5 equals 14. And so I get A is 2. And then we're going to go into any of the original ones. I'm going to choose A plus B plus C is equal to 3. So 2 plus B plus 5 is 3. So I got B is negative 4. So that means, well, we found the 3, but let's actually write the equation. Oh, you can't see that. Sorry. I need to pay attention just like at school, right? So y is equal to 2x squared minus 4x plus 5. This is what the equation that has those points would be. Now, we only have one example left. I know it's getting kind of long. I'm trying to keep these down to 20 minutes, and I'm a little bit over. I apologize for that. But since we only have one left, I just want to go ahead and get it done. So example 9, it's a word problem. This is how you might see it. I don't think this one's too very difficult. It says Kyle and Austin are taking the baseball team on a spring break road trip. They plan to rent a van so everyone rides together. Airport Rentals has a flat rate of $50 plus 10 cents per mile. Best Auto and Van charges $30 flat rate plus 15 cents a mile. How many miles can the team drive in order to be charged the same amount by the two companies? Now, if you write this as two separate equations, which you can say, okay, what is it? Best Auto and Van, no, Airport Rentals. Let's do that one first. Airport Rentals, Y would be equal to $50 plus 10 cents per mile. And then the other Best Auto and Van, Y would be equal to 30 plus 15 cents per mile. Now make sure that you're putting your decimal there to represent the 10 cents and the 15 cents, because if you don't do that, that's going to mess it up big time and all your numbers would be wrong. So at this point, we can use elimination, but I find substitution does the best. If we want to know when they're actually going to have the same charge, I just set them both equal to each other. And then solve. It's pretty straightforward. I believe you've done this in Algebra 1. I feel like we did it in Algebra 1 back in the day. Probably this, maybe not the same exact one. And you end up with, what is that, 400? Okay, so that's 400 miles. So if they're going 400 miles, it's going to be the same price, no matter which company they choose. So notice on part B, when would it benefit the boys to choose one plan over the other? Well, if they're doing 400 miles and it's the same, if you're going more than 400 miles, then you need to look at the one that has a less cents per mile. If you're going less than that, you want to get the one that charges more cents a mile. So basically, if the trip were more than 400 miles, so I'm going to write if the trip were more than 400 miles, they should choose airport rentals. Because that would be the more cost effective, because then they're only paying 10 cents per mile more rather than 15 cents per mile more. Now, when you finish with these notes, all you have to do is upload this to Shobi so you can get credit for that.